Okay, this question is about a line to ground fault, and we have to draw the equivalent symmetrical component network to represent the fault, and we have to calculate the fault current. So the first part to look into is that we are given the generator voltage as the line voltage, and then we are given the reactances in per unit. Now then they all have to be in the same units, so what we have to do is we have to convert the line voltage to its per unit value. Now the step for that is that you can convert the line voltage to phase voltage, but the base value will be same as what is the actual value in this case, because you have to assume the base value is something which is going to be 46 kV converted to phase voltage. So the main point is that the base value equals to the actual value. And if that happens, now if we have to find out a per unit generator voltage, that equals to the actual value divided by base value. Since they both are same, so you're gonna have a per unit voltage of 1 angle 0 per unit, right? So now we are ready to draw the network. Now it's a line to ground fault. So for a line to ground fault, it's called LG. You have all the three networks, positive, negative, and zero sequence connected in series. So for a generator, the positive sequence networks looks like that you have positive sequence reactance and a source. Okay, there we go, that's the first one. Then the negative sequence is have the negative reactance. That's how it is. And then the zero sequence have the zero sequence reactance. Now if we look at the values, the positive sequence is 0.2, and since this is a reactance, so there is a J 0.2 in per unit. Then we already found that in per unit this voltage is 1, and then the negative sequence reactance is J 0.1, and the zero sequence reactance is 0.25, so J 0.25. Now all these networks will be connected in series. So to connect them in series, what we do, we connect the end terminal of one to the beginning terminal of the next. So this is the end terminal of one, which is connected to the beginning terminal of second. This is the end terminal of second, which is connected to beginning terminal of third. All right, this is the end terminal of the last one. So this is going to be connected back to in the beginning, right? Now let's mark the current. So the current flowing here is IA positive. The current flowing here is IA negative. And in this case, it is IA 0, right? So what you can say is that all three of them are same. And then we will figure out how to find its value, IA 0. Right? So this is your network. The one we have drawn here is your third one. This is A, which is equivalent symmetrical component network. And part B is we have to find the fault current, and you can use the table to see what fault current equals to in terms of these currents. So if you refer to the table which has been provided to you guys during the class, so IF equals to 3 times IA positive. All right. So if we see these three, 1, 2, 3 are connected in series. So for finding this current, although they all are same, so either one of those currents, we're going to use Ohm's law, and Ohm's law is the voltage in a circuit divided by the total reactance. So total reactance is sum of these, 0.2, 0.1, and 0.25. And the voltage is 1 per unit. So this current will be 1 divided by the sum of the reactances. So IF equals to 3 times the voltage is 1 angle 0 divided by sum of the reactances. 0.2 plus 0.1 plus 0.25. So if you sum them up together, it brings you times 1 angle 0 J 0.55. Now J equals to an angle of 90 degrees, so it's 3 times 1 angle 0 divided by 0.55 angle 90 degrees. Right, and that brings you 3 times 1.82, so this is a times. And angle, so 0 minus 90 will bring you minus 90 degrees. Now 3 times 1.82 is 5.45 angle minus 90 degrees per unit. So this is your fault current.